Welcome to The Explainer, brought to you by Forge College. Let's jump right in. Today, we're tackling a topic that really separates the okay developers from the truly great ones: performance trade-offs and runtime constraints. Now look, I know constraints can sometimes feel like, annoying roadblocks when you're just trying to build cool things. But I want us to playfully reframe them today. These runtime constraints, they aren't annoyances. They're literally the unbreakable laws of physics for our blockchain engines. If you understand these laws, you can engineer applications that absolutely fly. But if you ignore them, well, your transaction crashes and burns. So let's dive into this and figure out how to master the physics of both the EVM and the SVM.
Right, so anchoring back to our previous lesson on contract execution and parallelism, we compared the EVM's sequential determinism, where everything happens one by one in a super strict order, against the SVM's parallel account access, which, as we saw, lets multiple transactions run simultaneously if they don't touch the same accounts. But here's the million-dollar question for today. How do these two very different execution models actually charge you for their operations? Basically, we're looking at how they pay the bill.
Here's our engineering blueprint for today. We've got 5 key areas. First, the cost of execution. Second, EVM, the opcode taxi. Third, SVM, budgets and padlocks. Fourth, the multi-contract stress test. And finally, tracing, debugging, and takeaways. Let's get to it.
Section 1. The cost of execution, EVM, and the opcode taxi. Let's get into it. Imagine you hop into a taxi, right? But instead of just paying for the distance, the driver charges you a fee every single time he turns the steering wheel, every time he hits the brakes, and yes, he even charges you just to roll down the window. That is exactly how the Ethereum virtual machine works. It uses this highly granular gas metering system, where absolutely everything, every opcode, every memory expansion, every storage modification ticks that meter up.
Let's actually see that taxi meter in action with a standard Solidity loop. Step 1, we declare a mapping, which acts as our persistent storage. Step 2, we pass in call data arrays. Now, call data is cheaper than memory, sure, but passing a massive array, it still costs gas per element. And step 3, well, this is where the meter truly spins out of control. The conditional loop write. If you use an on-chain loop to iterate through an array and write new data to storage on every single pass, the EVM charges you for every opcode in that loop. It's literally like asking the taxi driver to drive in a circle and drop off a package on every single lap. You're going to hit that black gas limit so fast and your transaction will just revert.
And this massive discrepancy right here, that is the heart of the EVM cost problem. See that tiny bar? That represents the gas cost of pure computation, basic arithmetic, checking a condition. But that massive bar, that's the cost of a storage write. Changing a storage slot from a 0 to a non-zero value is astronomically more expensive than just doing math. It's crazy. The EVM practically begs you to do math, but it heavily penalizes you for touching the hard drive.
So here's your absolute golden rule, your crucial takeaway for the EVM. Avoid unnecessary storage writes. In this environment, storage writes are like giant potholes in the road. You want to dodge them whenever possible to keep your gas meter low and stay well within your block gas limit. This is exactly why you'll see optimization patterns in Solidity that cache state variables in memory. Do all the heavy loop calculations there, and then only write the final result back to storage once.
Section 2. SVM, budgets and padlocks. Okay, let's switch paradigms entirely and look at Solana's execution model. If the EVM is that greedy taxi driver charging you per turn of the wheel, the SVM is more like a contractor who gives you a prepaid project budget, but puts strict padlocks on every room in the house while they work. It's a completely different way of measuring and constraining execution.
Let's define the core SVM metric here, the compute unit. Instead of granular per opcode microcharges, SVM compute units are applied at the transaction level. So you're essentially given a budget for the entire sequence of instructions. And honestly, this is incredibly freeing. It means you don't have to sweat over the cost of individual mathematical operations like you do in the EVM. The runtime just aggregates the work, letting you focus on the broader sequence.
But there's a catch, right? And it's a big one: account locking. To achieve its blazing fast parallel execution, the SVM requires you to declare upfront every single account your transaction is going to touch. So if your transaction touches accounts A and B, and my transaction touches accounts C and D, the SVM runs them both at the exact same time. Beautiful, right? But if we both want to write to account A, well, we get stuck waiting at the padlock. The SVM explicitly locks accounts from competing write transactions to maintain state safety.
Now, while the SVM doesn't punish storage writes quite as severely as the EVM does, it definitely has its own hidden costs.
specifically deserialization and host syscalls. When your transaction pulls an account to interact with it, the SVM has to read and deserialize that account's data struct. So if you're poorly packing your accounts or repeatedly deserializing massive chunks of data just to say, change a single Boolean, yeah, you're going to drain your compute budget incredibly fast.
So having looked at the opcode taxi and the budgets and padlocks, I want to pose a question to act as a bit of a palate cleanser here. What happens when we compose multiple contracts? I mean, it's one thing to do a simple token transfer, but how do these two engines actually handle complex, multi-step applications where one contract calls another which calls another?
Section 3. The multi-contract stress test. To answer that question, we're going to design an atomic multi-component update. Now, atomic simply means the entire operation must succeed as a single unit or revert entirely. There's no halfway. Let's see how our two runtimes handle a heavy, interconnected workload.
Here are the 3 modules our test transaction has to touch. First, a ledger update to change a user's balance. Second, a rewards calculator that triggers to see if this new balance earns them a bonus. And third, a notifier event that broadcasts the change. So, in a single transaction, we're balancing deep call chains against our resource limits. How on earth do we survive this? Let's contrast the winning strategies. If we're building this on the EVM, our strategy absolutely demands shallow call graphs. Every single hop between contracts costs gas, and if that rewards calculator does heavy math and multiple storage writes, boom, we'll get an out-of-gas error. We have to rely on small library calls and minimize storage, but over on the SVM, the strategy totally flips. We aren't worried about the math in the rewards calculator, we're worried about deserializing 3 different program accounts. The SVM requires tight account packing. We need to bundle the minimum number of accounts and compress our data to survive those deserialization costs.
And that brings us to a really massive takeaway. Identify your bottleneck before you build. Seriously. If your atomic design won't fit the runtime budget, whether that's an EVM gas limit or an SVM compute budget, you have to pivot. You must either move that heavy math off-chain or split your transactions up and just accept eventual consistency rather than strict atomicity. You have to design for the physics of the engine you're using.
Section 4. Tracing, Debugging, and Takeaways. Let's move into our final act. Because, let's face it, no matter how perfectly you design your multi-contract architecture, things are inevitably gonna break. When that transaction reverts, how do we peer inside these engines to figure out what went wrong and fix them?
The debugging experience is basically night and day, because the EVM meters at the opcode level, when things fail, it actually provides incredibly clear stack traces. You can pull a gas trace, see exactly which opcode caused the revert, and find your gas hotspots instantly. It's great. The SVM, however, aggregates compute, so if it fails, you don't get that granular trace. Instead, you have to rely on proactive SVM logs. You need to build program-level checkpoints and compute metrics right into your code so you can catch exactly where your account I/O or deserialization failed.
All right, to summarize everything we've covered today. Under the EVM, your metering unit is gas per opcode and storage. Your limit is the block gas limit, which means your architectural implication is to favor smaller loops and strictly avoid storage writes. On the flip side, under the SVM, your unit is compute units and account costs. Your limit is a per-transaction compute budget, meaning your architectural implication is to pack accounts tightly and minimize those heavy deserializations.
So if you're a Web3 developer transitioning between these environments, you absolutely must adopt these 3 core principles. 1. Meter-aware design. Know exactly what the runtime charges a premium for. 2. Lock-aware composition. Understand how your multi-contract calls are going to trigger account locks or deep gas chains. And 3. Runtime-aligned observability. You have to instrument your code differently to debug an opcode hotspot versus a compute unit bottleneck.
I'll leave you with this final golden rule. Treat runtime constraints as first-class design inputs. Seriously, don't build the application and then try to make it fit the blockchain. Design the application around the physics of the blockchain from day one. I really hope this explainer helped clarify exactly how these runtimes manage their limits. Be sure to visit forge.college to explore our other deep dives. But before you go, consider this. If runtime constraints are the physics of the blockchain engine, how does the actual shape of your data dictate how fast you can travel? Next time, we're going to apply these exact performance constraints to our next major topic, state models. You definitely won't want to miss it. Keep building, and we'll see you next time.